Welcome to the course on power quality. Today we will discuss this power quality improvement in solar energy conversion system as a case study. So, coming to the outline of presentation, we will like to discuss with the introduction, then we will talk about maximum power taking algorithm of solar PV system, then classification of grid integrated solar power PV system, then we will talk about with this classification with single phase grid integrated solar power photovoltaic system. I will talk about double stage grid integrated solar PV system, then of course, the single stage, and we will go to 3-phase grid integrated system. So, there we will again talk to double stage and single stage system, and then of course, we will like to introduce the PV battery based microgrid with grid synchronization, where we have a solar as well as battery with. So, coming to why we need really solar energy, the motivation, because of vanishing the conventional energy sources. It is a green energy, it is reaching the grid parity, means in the cost of the now solar is coming the same as the power available from the grid, and the argument that sun provides power only during the day is countered by the fact that 70% of energy demand is during the daytime hours, and at night additional methods can be used to generate the electricity. And goal is to decrease on our dependence on the fossil fuel. Currently 75% of our electrical power is generated by coal burning and nuclear power plant. It mitigates the effect of acid rain, carbon dioxide and other impacts of burning coal, and counters the risk associated with nuclear energy. It is pollution free and indefinitely sustainable. Then key technical challenges that affects the quality of power is in solar photovoltaic power generation are typically voltage fluctuation on the grid, harmonics in the grid, the DC offset, harmonic high frequency wave, reactive power, the voltage regulation, and the key technologies that affect the quality of power in solar PV generation are the low power factor, unbalanced grid voltage, then neutral current problems, and solar power intermittency and load management. Now, coming to the grid connected solar photovoltaic rooftop system, the grid connected solar photovoltaic rooftop system are installed on rooftop of residential, commercial and industrial premises. Electricity generated could be fed into the grid or used for self consumption through the net metering or feed in tariff, and CFA to be provided through the direct subsidy around 15 or equivalent interest subvention through bank. And what are the advantage of this rooftop grid interface system? Why we are going to this? It saves the transmission and distribution losses for the utility. It has a low gestation period. You can have even a month. You can install the plant of megawatt and no requirement of additional land, because you can use the rooftop. An improvement of tail end grid voltage and reduction in system congestion with higher self consumption of solar electricity, and it generates the local employment, and it reduces the power bill by supplying surplus electricity to local electric supply. Well, the battery elimination makes easy installation and reduce cost of the system, and no storage losses lead to effective utilization of power, and of course, local employment generation and power quality management, peak power supply and supply security, and performance verification under point of common coupling voltage, and indirect cost reduction by reducing the losses and minimizing the trips, and no energy storage element in the distributed power generation system, enhanced utilization for installed distribution equipment like transformer, distribution and line, and load profile flattening can be achieved. So, we have a two system, like you can have a standalone and grid interface solar photovoltaic system. In a standalone system, energy storage is must. The sizing and maintenance of the same is a big problem. So, it grid interface energy storage can avoid it, hence their cost, weight and maintenance is comparatively low, and grid interface photovoltaic systems are becoming cost feasible, and the recent installation shows their widespread acceptability. This is the typical an example of grid connected solar photovoltaic rooftop system, that you are having a solar panel on the roof, these modules, and we have of course protection devices with junction box, and you have an inverter which is with the isolation transformer, depends on, you might have a manual disconnect, and then it is connecting to the line, which can feed either to the load in the home appliances, or it can go to the power to the grid like. So, that is what as a conceptually, I mean you can think about grid connected solar photovoltaic system have a kind of configuration like. And India largest rooftop grid connected solar photovoltaic plant of 7.52 megawatt in Vyas. Well, if we classified the solar energy conversion system, we can have a standalone on grid interface, that can be also single phase, 3 phase depending upon the power level, and grid interface of course, which are in majority, because you cannot typically store the entire electricity generated of, otherwise you have to need energy storage. So, you can again have a classification single phase, 3 phase, and you can have a single stage, 2 stage. We will discuss what is single stage, 2 stage. Then you can think about the topology classification and the classification based on the control like. And when you come to like a 3 phase system, you can have a 3 phase 3 wire, and you can have a single stage 2 stage with the topology and control, and then you can have a 2 stage with topology and control. And we talk about 3 phase 4 wire, of course, that is also the distribution system. So, we can have a single stage 2 stage with topology and control configuration of this. So, you will just find, I mean typically of several kind of configuration, I mean in case of this solar PV generator depending upon the power level. Low power, of course, we take a single phase, and of course, if it is like a distribution, so we have a 3 phase 4 wire, but in many cases we have a 3 phase 3 wire like in industry or like a big typically premises like. Now, coming to, I mean it can be classified in 2 category, the typically the maximum power point tracking, you can call it, typically can be a load interface with the DC-DC converter in DC microgrid and or DC to AC converter for AC load, and can be have in standalone or AC grid interface system. Coming to maximum power tracking, because you have already made a big investment in the panel, so you like to use the maximum power, I mean, and this becomes very interesting challenging problem, because the solar insolation of solar PV go on changing in the whole day, and these are the typical characteristic like of power, because you will just see the power go on changing with the solar intensity, and this is the typically current and voltage characteristic, and this is power versus voltage characteristic. So, you will find that you have to move on the maximum power point, I mean under different solar insolation, and this happen probably in the daytime at different intensity since morning to evening or even at peak lunch time. The effect of change in insolation is the change in short circuit current level, change in open circuit voltage, and change in maximum power point voltage like, and certainly it needs for maximum power point tracking controller like. So, coming to maximum power technique, you have a lot of technique like hill climbing, or it is also called perturb and observe technique, incremental conductance method. These are the couple of conventional methods, but there are a lot of other technique like fractional open circuit, fractional short circuit current, ripple correlation, discrete time ripple correlation control, then current sweep, DC link capacitor group control, fuzzy logic based MPPT, and then ANN based artificial intelligence based maximum power tracking control. And now, coming to grid tied solar photovoltaic power generation system, I mean normally we use, of course, you can use any converter like either voltage source converter or current source converter, but voltage source converter are more preferred for solar energy conversion system with indirect typically cost reduction, and solar PV generation system remains utilized for more than 2/3 of the day. If the inverter used for SPV solar photovoltaic generation, power generation can be utilized as a voltage source converter during night time by taking active power corresponding to loss only from the grid, and SP solar PV generation during sun time, and the power converter involved in 3 phase solar PV generation can be fully utilized, and this will certainly indirectly reduce the cost of operation also. These can be classified into 2 main category: solar photovoltaic system feeding energy into the grid, feeds sinusoidal current at unity power factor in single phase, and feeds balanced sinusoidal current at UPF in the 3 phase, and solar PV system with the indirect cost reduction feeds extracted solar energy into the grid, and ensure several other features also, that it can compensate if properly controlled like harmonic reduction, it can provide grid currents balancing for 3 phase, and it can have a neutral current compensation if it is a 3 phase 4 wire system, and of course, you can compensate for reactive power also, because the inverter capacity never utilized fully, because you do not have a full generation all the time. Moreover, you still have a margin in the inverter rating also. So, coming to the typically starting from single phase grid connected solar photovoltaic power generation system, I mean we classified them like again into single stage and double stage, and further classify without battery and more popular due to cost reduction and weight, and storage battery. Base grid interface is normally used to feed constant power into the grid, so that the intermittency of the generation is not reflected on the grid and may help grid stabilization during power system tangent. These are typical example, like we have solar PV array with the for photovoltaic maximum power tracking of PV array, photovoltaic array. We are using typically here the boost converter, which is feeding the power of course on the DC link of this inverter. I mean, you can have a 1 degree of the freedom here. So, we normally like to operate this your solar PV array at maximum power with the help of this boost converter, and typically this inverter, I mean from DC link, it feeds the power to the grid. And how, I mean like it knows that how much power is coming. Normally we have a DC link voltage controller on the DC link of it, and that output of DC link voltage controller we consider the amplitude of the grid current, like and that really you can call it the power fed to the grid, and you can control this in the current control mode. So, that I mean typically current injected into the grid, this has at unity power factor, current is out of phase with the voltage, and typically even in spite the voltage may be distorted and voltage may be fluctuating, but still you can maintain the current sinusoidal and typically quite smooth current fed into the grid like or so. But of course, there can be further modification in the control. So, what it is shown here, I mean we have taken a typically another, I mean this is the DC link voltage control that you have a reference. If we typically in this control, if we, because typically in country like India we have a voltage fluctuating on the grid, but if DC link voltage we decide in relation to the peak voltage of the grid which we are getting from sense AC voltage, then the losses in the inverter can be reduced. So, that is the concept of course utilized here, because if voltage varying over a wide range, and this is the DC link voltage. Normally in single phase converter you have a second harmonics on the DC link, that is the reason we have to use low pass filter here, and then this is we feed to the PI controller. So, this we consider it as a one component. I mean like typically, I mean we are able to know how much really how we will stabilize the grid, that if voltage try to increase because of more solar power injection, then certainly the PI controller will increase. But along with that we have a, of course with the maximum power tracking we have a PV power, and from another this component from PV power, if we are able to take feed forward term, I mean like, and that because this needs the losses and this comes the power from there, then we are able to get amplitude of the grid current, and which we multiplied the phase achieved from the voltage which we are filtering also, of course this voltage from band pass filter, then we get the reference, typically the reference grid current, and we have a sense grid current and give a getting signal for this single phase voltage source converter in unipolar mode. So, that is typically the how the inverter is there, and this is the boost converter control, that we have PV voltage, PV current, and we are calculating typically the PV reference voltage. We have already DC link sense voltage which we are sensing already here and filtering. So, from this we can find out the duty cycle for typically control of boost converter. So, this is the control, like I mean to reduce the burden on DC link voltage control, to avoid the overshoot, we are taking here the feed forward term, and that really stabilize the system much faster, as well as no overshoot undershoot is observed on the DC link voltage, and we are able to reduce the losses if we are using typically like this typically the reference DC link voltage is correlated with the AC voltage amplitude, which we are doing here with the help of this factor. That also reduces like 3% losses, especially when voltage is fluctuating of the grid like that is usually. So, this is the typically the amplitude of AC voltage. We have a we are sensing the AC supply voltage, and then after band pass filter we are converting into phase and quadrature component, and from this phase component we are getting the template which really require for estimating the current, and then we have a reference DC link voltage in terms of your peak supply voltage which we got from here, and then we are able to have a PI controller which represents the loss in the inverter, and that gives the one component to us. And another we get of course feed forward component. This is what we are getting from PV power, I mean the equivalent amplitude of the current corresponding to that, and if we take into account, I mean the inverter output knows in advance that okay more solar power coming or less power coming, so that the burden on DC link voltage control is reduced, and then we are able to get amplitude of grid current, that is the loss of the inverter minus the power coming from the solar, and this minus represents that the current is out of the phase with the voltage. I mean we get from this, we know the typically this amplitude, and we already have a phase. So, we are able to get your grid reference current, I mean typically your IP into U, what we have defined the template previously, like this one. So, this give a reference current to us, and then we can sense the grid current and have a current control over it also. And this is typically the MPPT performance at different solar insolation. So, it operates all the time maximum power tracking, and these are the typical result on the, you can see on the power at different voltage like a 230 volt and 172 volt, but the TID of the grid current is maintained very well, and the power factor typically on the grid is also maintained unity. But why minus sign is there? Because we are feeding the power to the grid, and this is typically nominal voltage, and this is the voltage maximum voltage. You still you are able to get the less than 5% TID in all the cases or so, and you have a a smooth power flow to the grid of this like these are when you are having a solar insolation increasing, DC link voltage is constant, but when PV generation is increasing, so you will find the grid current is also increasing to feed more power. And if you have a solar insolation reducing, the your PV current is reducing, and then you are having a less current flowing into the grid like, but current remains the sinusoidal and in phase with the voltage, of course out of the phase with the voltage. And you can clearly see here how if voltage is reducing, there is a voltage sag, then accordingly the current is increased for the same power. If voltage is reduced, the DC link voltage is also reduced, and that reduces the losses in the system also. And similarly, if voltage enhances, like you have a swell in the voltage, according the grid current is reduced for same solar power, and accordingly DC link voltage is also varying, so that the losses in the inverter also reduce also. But PV generation have been constant during this case like. So, that is a typical case. Now, we extended that the basic concept to improve the power quality in the sense normally you have some local load like rooftop, you have a local load, some local load, and even you can compensate the local load because you have a capacity involved in the capacity already there in the inverter. So, we can even maintain the grid current sinusoidal and compensate whatever the either reactive power or harmonics is taken by the load, not only improving the power quality fed for the grid power, but even you can compensate the local load even for 24 hours, even the solar power generation is not there. So, you have again solar PV here. So, you have a boost converter for MPPT, and then we have what the current we have to put to the grid, that will be solar minus the load power minus the losses of the inverter, and that is we really feed to. So, then we have to modify the typically the control for that getting a. So, you have a maximum power tracking controller with the incremental conductance concept, which give the PV reference voltage, and then we use the control algorithm for voltage source converter, which ensures several features like feeding extracted energy into the grid, then reactive power compensation of local load, harmonic elimination of local load, and maintain the your DC link voltage of the inverter. And this is the of course maximum power tracking algorithm from which we are getting the reference, you can call it the PV voltage, and that is virtually come the concept of algorithm, that how you have to decide the voltage operating voltage of the PV array. In that case, and you are able to get the duty cycle from reference PV voltage which you are getting from here, and what you are having the DC link voltage which is known to you from the inverter side like and that gives from this duty cycle you are controlling the boost converter also. This is the control block diagram of the control. So, what we are doing here, we are sensing the load current, and from load current we are extracting its fundamental active component of current, and we have a DC link voltage, and we have a again amplitude of DC reference voltage in correlation with the supply voltage, which we are passing through band pass filter and then getting amplitude of it. So, this we have a PI controller, that is virtually the loss in the inverter, and you can call it typically getting a fundamental component of the, we are with the zero crossing detector on sample load, we get the amplitude of load current, that also have to be supplied by the typically coming from the grid. These losses also have to come from the grid. Only the solar power which we have a feed forward term from solar power, that really get put into the really grid from the solar side. So, the difference of these will virtually come as amplitude of the grid current, so multiplied with the phase from the voltage, you get the reference grid current, and you have a sense grid current, and you can give the gating signal to the inverter. For MPPT in the same manner, we have PV voltage, PV current, and from this PV voltage we are able to get reference voltage from MPPT controller, and then of course, we have a DC link voltage. So, we are able to get virtually here you can call it like a duty ratio, and comparing this duty ratio with the your typically your sawtooth waveform of carrier wave, you are able to get the gating signal for boost converter. So, that is typically the control, and this is the of course expression for maximum power tracking, where we are getting a duty cycle for in the case when power increases, power decreases, and the change of voltage, and then we are getting the peak of supply voltage, of course dividing by from getting the from filter the two component, and then we are able to get a phase of this supply typically voltage, and we are able to get a PI controller which represents the losses of the inverter from this, and then from these components we are able to get a reference grid current as shown the block, and this is typically the, you can call it the operation of solar PV array corresponding to maximum power tracking at different solar insolation level. And these are the typical results from this. I mean, you can just see the grid current is out of the phase sinusoidal current. However, there is a local load which have a non-sinusoidal current, and typically the inverter is compensating for that along with the solar PV generation, and the TAT of the grid current is just only 4.3%, and the power factor of the grid is unity. So, some power it is feeding to the grid here to the local load. This is the local load power and load current, and this is the power typically generated by you can call it typically generated by the PV array. This is inverter, and this is the typically the what you are having like a typically the PV voltage PV current like. And this is the case during the dynamics. I mean, like when you are having a solar insolation level changing, I mean you have here the accordingly the inverter current go on changing, and you will find the grid current accordingly go on changing. And then the if it is you have a voltage sag, voltage reduction, then accordingly you will find for a given power the your grid current or increasing like. But when you have even like let us say you remove you do not have a local load, you still go on generating typically, I mean now the grid current, and typically you can call it your inverter current will be the same because local load is not there, but you still go on generating the power without smoothly with no problem like. And when you have a typically the your over voltage in the grid, accordingly the adaptive DC link voltage is increased and you reduce the losses and the grid current is reduced like, I mean you can clearly see here. So, I mean the your control is make optimum in a way, so that switching losses or losses in the inverter are reduced by taking adaptive DC link voltage, and we are able to compensate the local load also, that we can do 24 hours utilizing the inverter for these other features to work as a active filter for harmonic elimination as well as the reactive power compensation for compensation of local load also, that you can do 24 hours from which the payback or the cost of the inverter can be recovered like. And this is the typical which we mention it how much you can save. There is a substantial saving, I mean like at least on lower voltage where the losses are in the inverter are reduced, and that much extra power you are able to generate typically in kilowatt. I mean when voltage AC side voltage, of course solar generation is same, but AC voltage is low, but of course at rated condition also you are able to save something, and because you have to select the DC link voltage in, let us say you keep the typically the fixed DC link voltage, but that you have to select corresponding to the high voltage like maximum voltage of, I mean like a 270 volt, for which you have to select the 425 volt. So, if you keep all 425, certainly you will have a more losses in the inverter at lower voltage. So, this optimum or adaptive DC link voltage reduces certainly the, I mean the losses, and you get the extra generation in adaptive, and this generation, I mean you can call it is substantially different in case of lower voltage like. The typical case of single stage system, in single stage system of course, you are able to remove the boost converter. So, what we do it from MPPT we get the typically the output of PV array, which is the DC link voltage of the inverter, and the same we are able to have to control by the inverter itself by using a PI controller on that, and then that gives the amplitude of the grid current. Typically we have a phase, then we put the power for grid injection like. So, this is typically the control here, that you have a DC link voltage, I mean like coming at typically sense DC link voltage, and you have a reference DC link voltage from MPPT controller, because that corresponding to MPPT you have to maintain DC link voltage, and then we have a PI controller, so which represents the loss component and maintain the maximum power, and then we have a feed forward component, I mean from amplitude of the voltage and the PV power already we are getting for MPPT, and that give the typically another component, and we subtract the loss of the inverter, that give the amplitude of the grid current multiply the phase of the obtained from the supply voltage, sense supply voltage. So, we get the reference grid voltage, we have a sense grid voltage, and we generate the by PWM control current controller, we are able to generate the gating signal for all 4 devices of this voltage source inverter like. So, this takes care, you can call it like MPPT, as well as it also takes care typically the fast response of the your system without overshoot or undershoot, because if there is undershoot overshoot in DC link voltage, maybe you might be really losing some generation, because that voltage is required according to maximum power tracking also. And this is how you are really having a reference DC link voltage corresponding to maximum power tracking and the amplitude of grid voltage, and you are able to get template from here, and you are able to get feed forward term, and then these are the typical results by this system, and you are able to get TAT around 2. At rated voltage around 2.9%, even at reduced voltage of 171 you are able to get like 1.8% TAT, and if when you go even 270 volt you are able to get even the TID of 4.1% or so. Why it is increases little bit? Because current here it is reduced to lower compared to the lower voltage TID, because current is high, because ripple current is almost like a constant there, and you are able to get almost the unity power factor under all operating conditions to the power fed to the grid like, and it operates successfully when there is a decrease in grid voltage, and you are typically able to have increase in the grid current for same power generation. And you can see when there is a increase in the grid voltage, you have a decrease in the current for same power generated from the solar PV photovoltaic array. And then you can just see like here, even if you reduce the power generation to like power generation, then accordingly the grid current is reduced. If you increase typically here the solar generation, then grid current is accordingly increased like. Now, coming to typically like this single stage system, can we do typically this load compensation? Yes, you can do the load compensation for utilizing the inverter. Now, the inverter might be doing like one is MPPT it is doing, another it is compensating the local load also, like and feeding the sinusoidal current to the grid after feeding the local load like also. And this is the typical algorithm that we are taking a sense voltage, we are estimating after filtering it to two component from which we are getting typically here of is two component like typically from here, and we are able to get the phase from here like typically. Well, again we have a here the from solar PV MPPT algorithm, we are getting reference PV DC link voltage, because it is a single stage system. We have a sense DC link voltage where ripple second harmonics normally there because of single phase inverter, so we use the low pass filter, and then we are able to get PI controller, so this P component take a loss. Then we have a feed forward component from the PV power, that is of course the you are typically feeding the power here, and then you have a load current from which you are getting fundamental current through this typical algorithm, and that fundamental current really required to be fed from the grid only. So, then with this we are able to get amplitude of grid current, and we have a phase already from the typically from voltage. So, we get the reference grid current, we have a sense grid current, and we have a current controller to feed to the grid like also. So, that is typically how we are from MPPT, how we are able to get a reference DC link voltage, and how the amplitude of the grid voltage, and then how the template phase template and quadrature template, and then we are DC link voltage control the PV voltage correspond to MPPT, and that we represent the loss component of the inverter. And then of course, from the load current we extract the typically from this the fundamental current from this, and because we use the typically the filter here, and then we get the fundamental current active component that really implement the control. So, this is typically MPPT for correspond to different solar installation level or because of the MPPT algorithm, and these are the typical results you can see here. You are able to get the TID typically order of like a 4.3%. These are typically correspond to the less than even 5% well, and you are able to get like a typically like here the power factor of typically order of almost unity on the grid like also, and you are able to have even a load compensation also. This is non-linear load, it is a grid current, and that grid current TID where the load current TID is quite high, and then you are able to have a unity power factor on the supply. In spite the power factor of the load is 0.191, so as the harmonics as well as the active power or and reactive power of the load is supplied by the this same voltage source inverter, which is generating which is converting the solar generated power putting to the grid, as well as it is providing the active filter function also, and as well as it is doing the MPPT also. So, all tasks this inverter single inverter is doing, and you can clearly see the result here. If you have sag in the voltage, of course, the grid current will increase for same load constant also, and where you have like a increase in voltage, that is swell, and you are able to still give the quite good compensation local, and the grid current certainly reduces for a given power or same generated power, and that you can see how the if grid current is changing typically if PV generation changing, how the grid current is changing, and if load is completely removed, then the grid increases because the whole power now earlier partly power was going to the local load, now whole power is going to grid now. Now, coming to that was for single phase system. Now, coming to three phase grid connected system, we have here again the boost converter for maximum power tracking, and we have a three phase inverter feeding the power to the three phase grid. Here also we use the control in a manner that these currents should be sinusoidal and out of the phase with the typically the grid voltage, and we should have MPPT from the solar power generation. So, these are typical for a given conditions, this is the design of the component of this total system, and then here also we have the again solar PV generation, we are able to get this feed forward term, because response of the PI controller is not affected, and we have a DC link voltage and amplitude of DC link voltage. Even this two stage system, we are deciding from amplitude of the AC voltage, which reduces the losses in the inverter. We put PI controller here, and that we call it loss component. This is the generation, and from this we are getting grid current. We have a typically the phase of the grid current from the typically from the sense voltage, and then we are able to have a feedback grid current. So, we have a control signal for 3 phase, and this is the MPPT how we are getting from PV voltage PV current, and we get the PV reference voltage, and we have a DC link sense voltage. So, we can have a duty cycle and compare with the sawtooth. So, we generate the signal for the boost converter for MPPT, and this is the algorithm how MPPT really work. Using this MPPT algorithm, and to decide the MPPT voltage correspond to that. And once we know the PV voltage, reference PV voltage, we have already DC link voltage. So, we can get the duty cycle from here, and this is the amplitude of the your AC voltage we are getting from sense 3 phase voltage, and then we can get you can call it the template in phase with the supply voltage. So, that you maintain the unity power factor current in the supply side, and then we have of course, the reference DC link voltage we decided corresponding to the amplitude of voltage. So, that losses in the inverter are reduced to minimum. There is optimum voltage between the DC link and AC side voltage of the inverter, like for which losses are. So, these are the of course, loss calculation for regulating the DC link voltage, because this for regulating DC link voltage, some power have to come from the grid side to represent it as a loss component, and then we have a feed forward term for PV generation from this, that is also amplitude, this is also considered part of amplitude, and then we have of course, the reference grid current loss minus the PV generation current equivalent, and then we can have a 3 phase reference current. Typically from this is the amplitude, and we have a phase from there. So, you have a 3 phase reference current and generating the current controller, the PWM signal. And this is typically the MPPT operation of the solar PV simulator for the 2 solar insolation level. So, it work over a varying solar insolation level all the time at maximum power. These are the typical results. You can see the TAD virtually at even lower voltage of 350 is 1.2%. In spite the voltage TAD was 1.8%. So, it is lower than that, and here also even at 416 volt, that is a standard voltage, your TAD voltage 1.9%, but you have a current TAD 1.4%, and here it is you have a higher the voltage with the TAD 2.8% of this. So, it is capable of operating over a wide voltage range on AC side, and power factor remain unity in all the cases, like of this typically of this system like. And then you can see here the effect of typically even of varying solar generation, the grid current is accordingly changed, and typically if even the you can call it if voltage changes, then also typically the grid current changes, like that is the typically you can call it the voltage sag condition, or it is over typically voltage reduction, like, and it work very well over a wide voltage range, and we certainly take adaptive DC link voltage which reduces the loss in the inverter, because your AC voltage is varying very wide range. So, it is capable of generating the power, and inverters we modify the control in a way that inverter does not trip in that case. And this is the concept of the let us say optimum DC link voltage. Here you are keeping a fixed DC link voltage, you are keeping optimum DC link voltage, and you can see the typically with fixed DC link voltage and the ripple in the grid current with reduced optimum DC link voltage, like, and accordingly because if voltage is reduced, your losses, conduction losses or switching losses are, especially switching losses are reduced, like. Now, this is typically the concept with adaptive DC link voltage, that we are able to get little more generation, like typically around you can call it in place of 5.5 2 kilowatt, we are able to have typically around 6 kilowatt. So, that much reduction in the losses compared to the fixed DC link voltage, we are able to get in adaptive DC link voltage, like. Now, this is typically the case of 2 stage system, we are using boost converter for MPPT. Now, this inverter is not supposed to only convert the solar power into the AC power, but is supposed to compensate the local load for 24 hours, even if there is no solar generation, and we have a grid current sinusoidal in phase with the voltage, like. These are typically the control that we are sensing the load current, we are extracting the fundamental of amplitude of the load current active component which is in phase with the voltage, and that we are doing for all 3 phases. The load may be unbalanced, that is the reason we are putting balancing, adding the all 3 active component amplitude divided by 3. So, that gives the kind of averaging or load balancing, and then we have a DC link voltage here, we have a reference DC link voltage, we are having a PI controller which represents the loss here. We are getting again feed forward term from PV power, that is also represented in terms of the current amplitude on the grid side, and this is the net what we are really supposed to have the current in the grid after the losses and after typically the load feeding the load locally, and we have a phase. So, we get the reference grid current, we have a sense grid current, and we have a current controller to give the gating signal for voltage source converter like So, that is typically how the control this is of course the maximum power tracking algorithm for which we are able to get reference PV voltage, and once you have a reference PV voltage we are able to get the typically the kind of duty cycle for the boost converter which like implement the MPPT, and this is the amplitude of the grid voltage from sense voltage. These are the template which we are getting corresponding to the in phase and quadrature, and typically this is what we are getting like a for the extraction of fundamental of the load current like. So, and this is a loss component, and once we form the block diagram we get the amplitude, then we have phase for A, B, C. So, 3 phase reference sinusoidal balance current in phase with the voltage we are able to, and sense grid current we are able to get the current controller the operating inverter and compensating this the current, and we put a current controller over this, and we are able to operate this system typically for the purpose of this total compensation. So, you can see like how the 3 typically grid currents are here the balance and you are able to maintain the TAD very well of the current of less than typically even order of less than 2% in all the cases, and these are the load current you are able to provide the compensation grid current, and these are the inverter current, and you can find out the grid current TAD is 3.9% in spite the your load current TAD is 28%. So, this load compensation it is providing, and you are having a unity power factor on the grid in spite of you have a large harmonics here and the inverter current because you have active component it has a harmonics of the local load, but still the power factor on grid side is unity, and you have a typically the unity power factor on the load means the grid current is in phase with the phase voltage like. And this is the case when you are really have a suddenly the load removal on one particular phase. So, with this you will find the grid current increases because local load is consuming less power. So, the power which was fed to the local load is also fed to the grid now, and when you apply the load certainly grid current reduces because you have a fixed solar power generation and this is the typically you can think about how the DC link voltage change accordingly, and you have a dynamics, and then typically the solar power generation how the PV voltage is changing accordingly like for maximum power tracking. These are of course maximum power tracking at different solar insolation level, and it operates all the time at MPPT also. So, this is typically a single stage system where the inverter is supposed to do maximum power tracking also by maintaining the DC link voltage, that is the PV voltage also. It convert this DC power into AC power and compensate the local load also. So, that the grid current is your a balance sinusoidal as well as in phase with the voltage. So, perfect is maintaining unity irrespective whether you have solar generation or not, it is feeding the local load as well as the losses of the inverter to work as a typically as a compensator also. So, we have a typically load current for A phase, and we are able to extract the fundamental out of it. Similarly, we do the B and C phase, and for load balancing virtually we take average of this, and we have a virtually here the DC link voltage controller typically which represents the loss component, and we have a feed forward component from PV power. So, we get all 3 components here virtually, and from which we are getting amplitude of the grid current. We have a phase virtually the voltage which multiplied to get the reference grid current, and we have a feedback you sense grid current. So, we have a current control to get a gating signal for the supply, and of course, from sense grid voltage 2 line voltage only we are able to calculate all the 3 phase voltage as well as to generate the phase and quadrature template, because you require phase as well as quadrature template here. For 0 crossing you require quadrature component, and for typically for reference generation you require phase template also. That is the typical control algorithm which takes load compensation as well as the maximum power tracking of the solar PV array, and this is typically the maximum power tracking corresponding to 500 watt per meter square and 1000 watt per meter square, and this is clearly you can see the grid current which have a TAD of 1.8%, this is the your load current which have a TAD 25.6%, and you are able to have a unity power factor on the grid where the power factor of the load is low because of the harmonics, and you have a like a inverter feeding certainly the more not only the I mean the local requirement of the reactive power. However, the grid you do not have any reactive power or harmonics in that case like. And this is the typical case like when you have a unbalanced load, not only so A phase do not have a load, but you can say grid current are balanced, and you have a typically here you can see your load current TAD is quite high. However, the grid current TAD is 1.9% and the grid power factor is unity. In spite the load power factor is quite low of 0.72, I mean like or so. So, it give a you can call it like a load balancing as well as the harmonic elimination, I mean, and on the so it is compensating, you can call it load locally here like, and this is the typical you can call it like here the you are again linear unbalanced load and the but grid current are balanced, and you are able to get hardly a quite low TAD of the typically of the grid current about 1.8% or so, and you are maintaining the unity power factor of the grid in spite your load power factor of lagging is low. So, under solar insulation variation you can clearly see it that you are able to have a of course, the increased grid current for all the 3 phases, and when the solar PV generation reduces the grid current also reduces like. And then when load is removed the grid current is increased to accommodate the same power like, and when load is applied so less current flows into the grid, but current of the grid remain balanced sinusoidal and typically in unity power factor in phase with the voltage like. So, this is typically the 4 wire system with the single stage where I mean because normally in 4 wire you have a neutral current caused by the non-linear load. So, it is doing the MPPT, it providing the your typically the load compensation to maintain unity power factor current, sinusoidal current, and the grid current elimination is also taken care which is really generated by unbalanced load or maybe single phase load connected across the. So, the inverter is doing that with the additional lag it eliminates the neutral current like also, because there was a problem of neutral current bursting. So, that solar PV system takes care of that like also, I mean on all these compensation are provided. So, you have a MPPT algorithm I mean which have to be give a reference DC link voltage, but it is a typically single stage system and the your control algorithm doing all these functions. So, that is MPPT you are able to get virtually here reference DC link voltage. This is the control that we are getting 3 phase load current, we are getting a fundamental out of it and averaging it we are getting a per phase base of amplitude of the load current. Then we have a feed forward term corresponding to PV generation and we have a loss component from PI control on the DC link like. So, that give us like net active component of current I mean the grid current we have a phase multiplied with it. So, we get a reference grid current and from this of course, with the sense grid current we are able to get a your getting signal 4. So, for 4th lag we have a typically reference corresponding to neutral current is 0 and this is the typically sense neutral current of the grid. So, which maintains 0. So, it means the load neutral current is supplied by the 4th lag of the inverter locally. And typically I mean you can call it like what we have a feed forward term and we have it this typically here the all these functions by the control algorithm, and we estimate the amplitude of the voltage, then we estimate the phase template, then feed forward term of the inverter, and then we get a load component by using that typical filter fundamental component, and then we get the reference current, and these are the typically you can see 3 phase grid current, neutral current is 0. However, the load have a some small load neutral current and you are able to get like a quite good typically of the grid current power factor unity, where the even the load current power factor is low in that case. But when you are going to be typically a non-linear load, okay, 3 single phase, you have a reasonable neutral current which is compensated by inverter current, and these are the 3 phase grid current balance and neutral current is almost quite negligible, and you are getting a typically the TAD of grid current only 3.9%, where the TAD of the load current is around 45% also. And this is the typical case you can think about the grid power factor unity, where the typically the grid load have a reasonable harmonics in that case. So, that is typically the dynamics results. I mean like you can say even the typically load is unbalanced, is still able to make the balanced sinusoidal supply current like, and load is removed, load is applied. If load is removed, so it means the little more power fed to the grid, the grid current increases. When load is applied, there is a reduction in the grid current because less power, the solar PV generation is there, but you can see the neutral current compensation of the source is because the inverter is generating the opposite of neutral load current here typically in balanced and unbalanced load also like. And when you are having a solar generation varying, you according to your supply current go on changing and the load current remain constant. And similarly, if the solar generation increasing, the certainly grid current increases with the fixed load on the point of common coupling. So, coming to typically like here again this double stage system for 3 phase 4 wire. So, here we do the MPPT from the boost converter, inverter is supposed to do neutral current compensation, load balancing and harmonic elimination and the load current balancing like and this is the typical control that from the load current we are able to get typically extraction of fundamental current, and for all 3 phases. So, we get the typically here the equivalent load current here, okay, and this is the coming the from typically DC link voltage control loss component. So, we get the reference grid current, and you have a typically that is for phase, this is for quadrature for voltage regulation, and we get here the both template phase and quadrature. So, we get net current. So, we are able to regulate the voltage also by reactive power compensation by modifying this control like, and these are the typical result that you have a grid current balance, and even the load have been unbalanced. You can say the load balancing is also created by there, and you have a typically even a unity power factor of the grid here. Like in spite your load power factor is low. And if it is a non-linear load, you can clearly see, so still the grid current is sinusoidal balance, and even in typically the your neutral current is also reduced here, and TAD of the grid current is 4.3%, where the load current TAD quite have 37.4% like also. And when you have a solar insolation change, accordingly your typically or increase or decrease accordingly the inverter current go on changing like, and you have a grid current is still sinusoidal balance, even the load changes increase or decrease, and neutral current compensation is also taken care in there, and load removal and accordingly neutral current, and the PV generation typically load is removed accordingly how the control signal are modified typically for all the phases, and you can just clearly see the how the grid current accordingly changing with the these are the control signal of the algorithm which are estimated. Now, we will be like to discuss like the introduction of the battery to make it a concept of microgrid. Now, if you have a putting a battery, then we have a typically line inductive supported system, UPS features also we can have. So, that we can call it like a all the benefits comes in that, and we can have of UPS all features along with the solar PV generation also in this case. So, this is typical interesting case study. You have a solar PV generation, on DC link we are putting the battery, and we have even a local load also. Now, this battery is able to meet the intermittency of solar generation, intermittency of the load, and intermittency of the grid, because in the country like India we have sometimes we do not have grid, but load is can be committed because you have a PV generation here. Already battery power is also there, even the PV generation increases or decreases. So, the and moreover when it is typically grid is available, you can feed the constant power to the grid. The effect of load variation solar PV generation also can be avoided by this energy storage of the typically the battery like also. But we have to of course synchronize also when grid comes back and this inverter to float into. So, that is for corresponding to maximum power tracking how it goes, and this is a control corresponding to when grid interface system is there. So, you are getting amplitude of the voltage and phase, and you have a again feed forward term, and you are getting from load component. So, from this we are able to get typically the reference grid current, and we have a current controller which typically, and this is typically you can call it how if it is a your islanding mode. So, you have a typically the voltage, you have frequency, you have voltage. So, you have voltage control mode, it generates the reference voltage, and you have a feedback voltage of the inverter that becomes the reference, and you get the getting signal corresponding to sense inverter current. So, it feeds the load when the grid is also not there, and when grid comes you just go to the angle voltage frequency and angle should match. So, that is the how the angle is matching towards from the PI controller, that change the frequency slowly and it comes, and once phase frequency and magnitude all are matched, then we change over the switch from islanding mode to the grid connected mode, and it is operate in grid connected mode. First we have to check whether grid is in within a specified range or so. So, that is typically the algorithm how we are getting PV typically MPPT voltage PV voltage corresponding to MPPT algorithm, and that is typically the implementation that we get the maximum power tracking typically at solar PV two different solar PV generation like and this is you can clearly see here the typically in case of your islanding condition the voltage is sinusoidal in spite of feeding the non-linear load, and with the PV generation fed to the battery, part of the power fed to the load, remaining power goes to the battery, but if generation is less certainly power comes from the battery. So, this islanding case you can see clearly very good quality of voltage in spite feeding a non-linear load. So, you have a TAD of the voltage 1.5% when the TAD of the your load current is even 32% or so, and highly non-linear load you are fitting with the low power factor. And then this is the case for synchronization. You are operating in islanding mode with the load, and load is not affected because load voltage was already sinusoidal. When the grid appears here, and after few cycle you are able to synchronize here, and the grid current is start appearing, and how the angle is matching towards that, where you close the switch and grid current is start appearing like. And then here you can say the grid current, but load current is not affected, load voltage is also not affected even during the islanding mode as well as synchronized mode like also. And this is the typical case like when you have a TAD of the grid current 1.4%, which is less than the voltage TAD. I mean clearly you can see here, and this is when the case like typically the voltage is disappearing, but the load current and load voltage are not affected, I mean islanding mode. And this is the case when your solar PV generation, how it is just changing from one mode to another mode or so. And these are the typically the operation at different voltage also. I mean it successfully fully operate with the quite good TAD of the grid current typically of 1.3% and 3.7% or so. Now this is the case of two stage system, and what we are having here now, we are putting battery with the buck boost converter, and of course the synchronous islanding, all those features are there, but putting the battery with the buck boost converter serve the couple of purpose that you now you can select the battery voltage at optimum level. Moreover, the battery you can block the second harmonics which are normally there on the DC link. So that is virtually the features here like. So this is the typical control that we have a from PV power, we have feed watt term. From the load current we are getting the typically a load component of current, and we from the here I mean we are able to get I mean typically the how much power we want to feed from the battery. So all three components decide the amplitude of grid current. We have a phase, so we have a reference grid current, and we really have a current controller for generation. And for islanding mode we have a reference load voltage, we have sense DC link voltage, and PI control we are getting a reference inverter current, we have feedback inverter current, and we are in islanding mode we are able to getting pulse generation. And of course, I mean like that this is how we do the synchronization. We first check the voltage in the margin, current frequency in margin, and then angle also in margin. Then we say we have to go towards like if it is not, we go to islanding. If it is within the range, then we go for synchronization and the operation with the grid connected mode, like that is virtually how we go. So we calculate amplitude of the voltage, then the template of the voltage, and then we calculate the typically the reference grid current like, and then we are able to get corresponding to amplitude of the grid current, and that gives the typically the you can call it feed forward term here adding to that, and net grid current, battery component, PV component, and then the load component, and we get the reference grid current from here. And this is corresponding to the MPPT, we are getting corresponding to around 99.9% of maximum power tracking. And you can clearly see here when the load voltage was there, you can see the yellow one, I mean, but grid appears virtually here, and after matching the signal you are able to connect the typically the grid here where the current is start typically appearing of the from there, and the power even start taking from the typically from the battery also. You can feed the constant power and the synchronization from here to here about the grid current, but load current is not affected, load voltage is also not affected. I mean like, and when the grid disappears, again the load is not affected. I mean suddenly load voltage remains the same, and you can clearly see the load current is not affected as well as load voltage are also not affected. And this is the case typically you are getting grid connected mode 2.3% TAD, even the load current TAD was quite high. And when typically you have a solar generation outage, you can call it in the night, then still the you are able to feed the load with the sinusoidal current. So it work as a active power filter, this inverter in this mode also. Now coming to the concept of three phase, that we have a now battery putting with the three phase. So here also we have a concept of synchronization. So you can call it we are I mean the we are able to provide the uninterrupted power for the non-linear load. I mean like even the grid is not there because you have generated some power in the battery along with the PV generation, and when it is grid connected you can feed the constant power to the grid. I mean whether the intermittency of the variation in the load, variation in solar generation is taken care by the battery. So those kind of interesting features are there with the energy storage in that case also, and you are able to operate in UPS mode also. Of course, you have to use the control algorithm for filtering typically the voltage also, if voltage are distorted, and for synchronization. So you can clearly see if we are not switching on the inverter how the voltage are distorted because of non-linear current, and when we are switching on the inverter, the even the typically the voltage profile, I mean this is the synchronization, this is typically islanding, and how the synchronization take place. I mean like here the voltage appears here, and you just connect the grid but the load is not affected. Load current is still gone feeding from, because you have a battery available and the extra generation go to the battery, and if power generation is less, the power taken from the battery. And you can clearly see when there is no switching on, inverter voltage are distorted because of nonlinear load. When inverter switch on, you can see the voltage and current and voltage are 3 phase in phase, and of course, inverter takes care of the harmonic compensation locally also. And this typically is the case when you have a solar generation missing here, but still the load compensation is provided by the inverter. Also, in all the cases when solar generation start coming, you start having the typically the grid current feeding, like all those features means it does not matter whether when the solar power generation start coming, to start feeding the power to the grid or to the load. And you can see for islanding mode, you have quite good sinusoidal voltage with the quite good TAD, in spite you are feeding the highly nonlinear load like Thank you.